Hey, physics students. Going to give you a little tutorial here for how to do this universal gravitational lab. I am going to assign all of you one of these central bodies, either Jupiter, Saturn, Uranus, or that's it, actually, because I'm going to do the sun to show you how to do this. First thing we're going to do is I am going to cut and paste this into a new spreadsheet I'm going to mess with. You can do this in Google Sheets as well. Everything works the same, I think, in terms of all the little tricks. I left one empty line here because I want to go back to this document. I also want to pick up this line here and put that up top. And that looks good. Okay, so I'm going to go ahead and close this, or just minimize it down there. Okay, so first thing I'm going to do is I'm going to fill this stuff in, but I'm going to use the as much of the functionality as I can of a spreadsheet to do that. So here I need the period in seconds. This is the period in days. So to convert this number of days into seconds, I would have to take, I'm going to go up here into my little function thing. Again, Google Sheets works very much the same as this. And I'm going to put an equal sign in there to let it know that I'm going to do some math. And then I want to take what's in cell E2. I'm going to type E2. And then I need to multiply that by, let's see, this is days. So there's 24 hours in a day times 60 minutes in an hour times 60 seconds. That's 86,400 seconds in a day. That's a fun fact that you end up knowing if you're a physics teacher. So I'm going to hit enter there, and that will give me that period in seconds. And here's the nice thing about a spreadsheet. Spreadsheets are smart artificially. And you can drag, once you have one in here, if you grab that corner and grab that down, it figures out what you're up to, and it does the same thing. So if you click on this box, you can see it did the same thing with E3. It just figured that I wanted that same calculation, but done with the corresponding cell from each row. So that's nice. Great. Okay, now how do we find the speed? The speed of something moving in a circle is the circumference of the circle divided by how long it takes to go around the circle, or in other words, the period. So the speed is 2 pi r over the period. So let's see if we can do that. So that's going to be equal to 2 times pi 3.1159. That's certainly enough digits there. That's 2 pi divided by the, 2 pi times the radius. The radius is right here. That's in cell D2. D2. That's 2 pi r. That's the circumference of the orbit, or the distance all the way around, divided by how long it takes, which is the period in seconds, which we have in F2. And I enter there, and it does that calculation for me here. And then I'm going to go ahead and populate that column. All right. And you see, just to observe here, the further away these planets get, the slower they're going. So that's an interesting observation. How about the centripetal acceleration? Well, centripetal acceleration is equal to v squared over r, right? That's a thing that we know. It's on your formula sheet. So centripetal acceleration is equal to v squared. Let's see, the v, we just did that. It's in column, that's in cell G2. G2. I don't know if the little caret thing works here for exponentiation, so I'm just going to do G2 times G2 for squaring that. There's v squared over r. The radius is in V2. enter there. And I'm going to populate that column, those calculations. And gravitational field strength. So this is, if you go far in physics or you're just like a total nerd and you like to watch videos about physics and kind of read up on stuff that's out there, I'm a total nerd like that, by the way. No criticism there. You might someday run into the general relativity, the kernel of general relativity. We've talked about this a little bit at some point, is that acceleration and gravitational field strength are really the same thing. The units are equivalent. If you think about like our 9.8 meters per second squared, what is that? Well, that's the acceleration that something has if you release it in the gravitational field around the surface of the Earth. Now, we also use that number when we're figuring out how much gravitational force is there on something. You take on you, for example, you take your mass and you'd multiply it by 9.8. And really, you're not multiplying it by 9.8 meters per second squared. You're really multiplying it by 9.8 newtons per kilogram. It's how many newtons of gravitational force there are per kilogram of mass. So anyway, blah, blah, blah. The moral of the story, what I'm trying to say is that these two things are the same. Oh, dang it. So that's because it's doing, yeah, I know what it's doing there. So I'm going to well, you know what I'm going to do? I'm just going to say, you know what? They are the same. So they're the same. So I don't need to actually reproduce that. But if you were going to put those numbers in, I'm sure you could figure out, oh, okay, fine. So I'm just going to retype in here then. That's equal to also v squared over r. So that's v is in G2. So G2 times 2 over the D2. Yeah, that's where the R is. No, I'm not going to go ahead and do this. Oops. And all the way to the bottom. There we go. All right, now that's great. I'm going to minimize that. And look at my messy desktop on my computer. And I'm going to bring up, I'm going to do this in graphical analysis. I was going to open them both up, graphical analysis and Logger Pro also, but I can't actually do that. There's a weird software glitch that if I have Logger Pro open, it doesn't let me have XY, like manual data entry and graphical analysis. And Vernier, I actually have talked to them on the phone about that problem. And they know it's a problem, and they're just not really that interested in fixing it right now. Because who really wants to have both of them open at the same time besides me? No one. So what we want to do is the point of this lab, as described in the assignment, would like to investigate what is the nature of the relationship. And by that, I mean like what powers of what variables are proportional to what other things in this universal gravitation. We're not going to try to nail down in the lab what the constants or what the coefficients are. So in other words, we're trying to figure out like if this is just x and y, is this like a y equals some number times x? Is it a y equals some number times x squared? And so on. We're not going to try to figure out the meaning of the constant. We're just going to try to figure out the relationship of the variables. So to do that, I need to get some of the things in here. I'm going to need the period here. So column options. This is the period in seconds. I want days. And I think that I want it to use scientific notation. See how that goes. I can always change that. And apply. So that's there. And I want to go ahead and copy these. And I figured out the way, if you've had that problem like trying to copy things and you get a blank, one blank square at the top, if you click on the actual column header and then paste, it does it properly. All right, so there's that. And then let's see, what do I want next? Do I want the speed? Yeah, for sure. I want that. And I think I want that anyway. If I end up using it, yeah, all right. Oh, look at that. Speed, period. What kind of relationship is that? Talk about that in a minute. And let's make a new, I'm going to make a new manual column. I didn't do, if you're doing this in Logger Pro, all these things that I did here with the formulas and everything, you can do that in Logger Pro and just make new columns right there. Graphical analysis does not work particularly well for doing that. It's very clunky, the formulas that you have access to. Next thing I'm going to put here is gravitational field strength. I'm going to call that GFS. And the units for that would be newtons per kilogram. Those units are equivalent to meters per second squared. But we're interested in thinking about it as gravitational field strength right now. All right. And I think I also want to have the radius in there. That's the last thing that I want. So let's grab that column of data. On the header, paste that in there. And one more column would like to put in the radius. Orbit. And that's here. That. All right. That looks good. And so what do we want to look at here? There are two relationships that I want us to get a handle on here. The first is, you know what, I don't think I needed this speed after all, but that's okay. I would like to have understand the relationship between gravitational field strength. Now, what do you think that would depend on? How strong the gravitational field is around, in this case, the sun? Well, I think it should be pretty obvious, intuitive that it depends on how close you are to the sun, how strong that gravitational field is. If you're real close to the sun, it's going to be stronger, also a little bit hotter as you get closer to the sun. So I would like to investigate here, what does that relationship look like? Gravitational field strength, how does that depend on radius? So I clicked on this, I'm going to select gravitational field strength, deselect anything else. And then here I would like on the x-axis to see radius. And you can see that graphical analysis does an absolutely terrible job putting these numbers in here. Call Rainier again and complain some more at them. What I would like to do in my graph edit options, I would like to see the origin in this. So I'm going to turn this into 0, and I'm going to turn this into 0. It was pretty close to showing the origin, but I really want to see that. All right, so what does this graph mean? It means that as the radius increases, the distance from the sun increases, that gravitational field strength falls off very quickly. You can see how much bigger it is here for, this would be Mercury here, or the location of Mercury. And that's interesting. So what do we do with this? Well, I'm going to go to graph options again. And before we get away from this, I'm going to put a title on this. This is gravitational field strength versus radius. Or you could say distance. It's like the distance from the sun, or radius of an orbit. I'm happy with either one of those. It's There's my title. Why do I want a title? Because I'm going to snip this and I'm going to put it in my little lab report for this. And before I do that, I'm going to go to apply curve fit. Oh, that looks like a good fit, doesn't it? Not. And I'm going to go to, when we think that there's some kind of relationship, like with an exponent, this looks like maybe it could be inverse or inverse square or something like that. And those are options. But if we want log or pro, or graphical analysis in this case, to like run the numbers and figure out what is the best exponent that would relate these things, we can get it to do that. And then we can say, oh, I see it's a square relationship. We can see what that exponent is close to. Let me show you what I mean when I click apply here. So right here, you can see it's doing a fit of this type. Y equals coefficient. I'm not going to worry about what that coefficient means right now, but you should record it in your lab report. The x to the b power. And we're interested in looking here at what this b power is. And you can see that it's negative 2.031. Well, things in our universe don't follow mathematical models. They're not best described by mathematical models where we get these kind of crazy exponents, negative 2.031. So we humans come along and say, oh, this really means negative 2. So really what's going on is, how is gravitational field strength related to radius? It's directly proportional to radius to the negative 2, or in other words, inverse square. It's an inverse square relationship, and we're seeing that right here. So if you wanted to, once you see that, you can say, okay, so now I'm going to go back and make my curve fit, and I'm going to choose inverse squared. And you can see that's one of the few choices because that is a common relationship. And there we have that. And interestingly, I don't know if it's because graphical analysis is struggling with the scientific notation, but this number is pretty different from what we saw before. So that's interesting. So let's record that number. We're going to file that away and come back to that a little bit down the road. Okay, so there's one of the relationships we're interested in. The other one is we would like to look at the relationship between period and radius. So to do that, let's see. Here, I would like to have period. And here I would like to have radius. And there they are. And I would like to only have radius. So I'm going to turn GFS off, period versus radius. There it is. And get rid of that. And there's my power fit. And you can see that that landed right on the power of 1.5. That's kind of unusual for us. Usually we see things related to like the most likely things to show up when we're modeling the physical world and universe are things to the 1/2 power, if it's a square root relationship, things to the first power, if it's linear, things to the second power, if it's a square relationship. We've seen plenty of that, or maybe to the -1 or -2 powers. Those are the powers that we see often. This is weird. It's the 1.5 power. So that is correct. That is what you should get. And we'll come back to that again and see in our notes why that power of 1.5 is showing up. Now that means that period right here, that's what should be in place of y, is equal to some constant, worry about what that means later, times radius to the 1.5. If we didn't like having that 1/2 power there, we could square both sides of this, and then we would have period squared is equal to a constant times radius cubed. And if you wanted to see a straight line relationship, you could graph period squared versus radius cubed. And might see that in some free response question or something someday, where if you just want to get a straight line and find the slope of that to figure out what your constant is, then period squared versus radius cubed would be the way to do that. I think that should be good. that should help you get to the graphs, everything that you need in your lab report. Thanks for watching.